Okay, everybody. Well, let's get started with the seminar here. Again, thanks everybody for attending. I think today's speaker is Gary Smith. He's a senior expert systems engineer at Airbus Defence and Space, based in the UK. Yes, he's their overall architect for engineering processes and provides technical leadership for their defense transformation. He is as he stated, a systems junkie. And when asked why he does this stuff, he says, well, it's what I have to do. It's who I am. So I will present to you Gary Smith.
Thanks.
Thanks, Gary.
Okay. All right. Thanks for having me. Yeah. So I'm going to talk about towards an integration of system science, thinking and practice. There's a lot of slides. Some of these slides I'll be going through pretty quickly. Some of them I'll be spending more time on because there are certain things I want to get across. So this is the overall structure. Introductions, organising knowledge about systems. Then I'll go into organising knowledge about how we engage with systems. And then I'll be making some connections with actual practice. So a little bit more about my background in terms of where I'm coming from. Originally I was an analytical chemist. I've done some work on project management. I was a project manager for quite some time. I've done software engineering, systems engineering. I'm an INCOSE ESET, which is a certified systems engineering professional. I have an expert status. I'm the senior editor for the Systems Foundations part of the Systems Engineering Body of Knowledge. I've been associated with the ISSS for some time. I've done some stuff on biosystems as well, so I've published papers on cancer and inflammation and preeclampsia and COVID. And I have a lot of books across system science, philosophy, sci-fi and fantasy. I'm a big Terry Pratchett fan, if anyone knows Terry Pratchett. So this is the topic of our talk. Systems, they're everywhere and everything. And system science is about transversal knowledge and concepts across all of this stuff, which will help us to basically live better in the world that we have. When we look at some of the problems we have to face in terms of programs and projects, our levels of performance in large projects is actually pretty poor. Only 1% of big programs actually deliver to time, quality and cost. Our performance on programs in terms of addressing the challenges we see has not really improved over the last 30 years, despite the advance in systems engineering and project management. So I've drawn on the Chaos report from the Standish Group. This book I would really recommend. Is from Ben Flyberg. It talks about how big things get done. And there's a whole load of information on project management heuristics in there, lessons learnt, and he has this massive database of 16,000 projects. And basically, we need to improve substantially in terms of how we deal with all of this stuff. And there's certainly a relationship between complexity and our ability to deliver. Also, we have an even bigger problem, which is the planet we're living on at the moment. So we're living in the Anthropocene, climate change, massive issues on immigration. We're changing the very geology of our planet, and this is all because of us. Yeah, and this is leading to existential threats on the very survivability of the human species. There's this really nice statement from Ray Eisen, who's a big system thinker. I spy complexity and confusion, but I can organise exploration of it as a learning system. And system science is part of that. I'm going to talk about two dimensions of system science. And what I'm showing you here is just a very high level view of knowledge about systems. The context, the entities, the mechanisms and the emergent properties. And that is one overall frame. Behind that is an awful lot of detail, but that's the top level perspective on knowledge about systems. Then there's another dimension of system science, which is about engaging with systems. This boils down to essentially knowing why, knowing what, knowing how, and wisdom, which is an emergent property. And that framework overlays on top of the other framework. So knowing why is related to context, knowing what is related to entities, knowing how relates to mechanisms, and wisdom, as I say, is an emergent property. Systems thinking and system science has been something which has been developing over the last sort of 50 or 60 years, maybe a little bit longer. And I'm just giving voice to many of the people who have contributed to it. Andreas Hieronymo did a great paper in 2013 summarising all of this. I'm also going to emphasise Bogdanov, who did some work with something called techtology back in 1915 to 1920. Tom Stonia was an information scientist, and Bud Lawson was one of the original architects of ISO 15288, which is our systems engineering set of processes in the international standard. All of those people have been influential on me. These are some of the people that I've been engaging with on system science over the last 10 years. I won't say who they all are, but these have had a big influence on me as well. These are system scientists who have been participating within COSI in the international workshops. And this is a collection of people from the ISSS at one of our last in-person conferences. This guy here is an absolute genius. That's Len Troncali, and he's been studying general patterns of systemic processes, which he calls system isomorphies. Len's been working on this stuff for the last 50 years. He was also lucky enough to be engaging with many of the founders right back from the 50s. So an amazing group of people. I've also participated in several conversations at the International Federation for Systems Research. The first one we did was unity and diversity, and the second one we did was what is system science, and that's been influential on the stuff that I'm going to tell you about today. There's a load of knowledge in the systems domain in terms of system science, both in terms of theory and practice, and what we've been trying to do is trying to find a way of integrating all of this knowledge in a way which is coherent, and we've been using system science to actually do that. When we look at some of the founders and what they were saying, it's stuff like this. So formulate principles that are applicable to all systems, whatever their nature may be. Common patterns, laws and principles fostering a holistic and integrative understanding of reality. Exchange of matter, energy and transformation with their environment. Systemic interconnectedness and the flow of inputs and outputs. So this is some of the things that the founders said about the nature of systems. Transversal knowledge, which is universal and transdisciplinary to everything, whether it's chemistry, physics, biology, sociology, you name it, cosmology. And this is some work that Len did, Nature's Enduring Patterns, which is a publication back in the 70s. I have a copy of that. They're very hard to get hold of. And then there's knowledge about how we can be systemic. And again, these are some of the things that the founders said about it. The understanding of social systems, organisations and human behaviour can be greatly enhanced by applying general systems theory. If we look to the more practical side from Donella Meadows, it helps us to identify leverage points for intervention and navigate systems change towards desired outcomes. So these are the advantage of applying a systems approach in your engagement with systems. And there's this really nice book from a group in Finland called Being Better, which is about living with systems intelligence. That kind of summarises it really nicely. You know, this engaging with systems, being better. Yeah, reductionist approaches have got us to the world we live in at the moment. We need to now be more systemic in order to address those global problems and to be better in the delivery of our complex programs. And I'll talk more about how we can actually do that towards the end of the talk. Because without system science, we will remain alsystemists. Everything we do in project management and systems engineering at the moment is based on heuristics. It's all based on experience. I can see the connections with system science, but we haven't made that explicit yet. The premise is that by relating those heuristics to the system's foundations, we can turn those heuristics into actually science-based principles. So there are certain patterns that we see across all of these different domains of systemness. So there's this waveform, for instance, of integration, emergence, diversification, which we see in all of our systems. There are terms, like these terms from George Mobus, transversal terms that are again universal. Functionality is everywhere. States, we see it everywhere. Cycles, all of these different terms which actually apply across all different disciplines. There's these different levels of system abstraction, which Tyler Volk gives voice to in his Quarks to Culture book. And as we go up through those different levels of abstraction, we're becoming more information rich as we go up. Yeah? And things at a prior level come together to make that new level of abstraction at a higher level. And you can relate our traditional sciences across those different domains, so physics, chemistry, biochemistry, etc., etc. So systems science is a transversal set of stuff, a set of knowledge which goes across all of these things. And the premise is that with system science we can be more disciplinary across all of these different domains and also across all of the different functions and product areas which we need to bring together to create our systems. I'm an architect at Airbus Defence and Space, and one of the things I've been trying to do is to create an architecture for system science. Architecture is the process of taking seemingly diverse and previously unconnected components, taking into account multiple perspectives and foreseeing an integrated system with emergent properties that serve stakeholder needs. And utility and elegance are the measures of success. It's not just a pile. And good architectures facilitate opportunity. Good architectures make you lucky. Frameworks are required for integration. They provide enabling constraints. And the way we took alchemy and created chemistry was through the periodic table. This is how we organised the subject of our understanding. And there were, going from left to right, we did go through some iterations until we got the periodic table that we had at the moment. What I'm proposing for you in this talk is something which is in the middle. It's not quite that, but it's on the right direction. Did some work with Bridget Daniel Allegro quite a few years ago, and we had this idea that systemists would consider system concepts when interacting with systems in any situation. This would be analogous to chemists playing with chemical elements when interacting with chemical substances. So what we're talking about is systems transformation, but the thing that we're playing with when we do this work is we're playing with concepts. This was the systems tree. You'll have the slides afterwards, so you can interrogate these in more detail, but the top of the tree represents the attitude of the systems thinker, and the bottom part of the tree represents the things that the systems thinker thinks about, like functions and inputs and outputs and purpose, drivers, hierarchy, boundary, togetherness, those kind of concepts. We also had in mind the anti-tree. So these are traps in thinking, and these are unfounded concepts, because there's no such thing as nothing. Even nothing is something. I talked about Quarks to Culture earlier, and Tyler Volk's grand leaps in what he calls complexity. And he had this idea of combogenesis, which is the emergence of systems. Combogenesis has many other terms which are similar to it, like metacriescence, ontogenesis. It's the birth of systems. And in Tyler's book, he had this nice diagram showing things of a prior level coming together to create new things and new affordances for new relationships. So when you put atoms together, you build molecules, and those molecules then have the potential for different interactions that you can't get at that lower level. So that's the idea. Things of a lower level coming to make new things at a higher level with new affordances for new relationships. And there's a model called the relational holon, and I'm going to explain using Tyler's diagrams how that actually happens universally. This is a universal model applicable to all systems. So we've got 4 parts coming to make a new whole. So here are the parts, and the parts are signaling. So everything in the universe is signaling, sending out signals. And those signals, when they interact with something which is capable of receiving those signals, there's an informational event, the potential for an informational event. So here you've got the signaling between those parts, and that's had an influence on the awareness of those parts. Their actual state has changed. For instance, a photon of light could have been absorbed, and the atom has changed into a different state. When you add new information to an existing structure, you increase its complexity. Now, when you have that change in state, what happens then is you get forces coming into a play, either repulsive or attractive. And those forces then lead to actual bonds between the parts. So what's happening here is you're actually getting, the forces are directing energy and mass to create new holes, and those new holes have new signals. So what we've got there is essentially information, knowledge, forces, and the manipulation of energy and mass in actual physical transformation. And this cycle goes all the way from quarks to culture in terms of those different layers, but it also happens within a layer as well. By adding more and more of the same components within the same organizational principles, you can create new elements by adding more protons, more neutrons, or you can create new molecules by adding additional parts and bits on. But we also see this in our day-to-day interactions in terms of our social systems as well. That holon is also at work in our actual scientific process as well. So you've got new information coming to form new knowledge. Principles are actually the forces that we utilize in terms of practice. And another source of knowledge is heuristics. Heuristics are purely in the empirical domain. It's learned from practice, but scientific principles are derived from your theoretical models. And that's the difference between the two. But there's a feed forward and a feedback throughout this process. And we see it in the scientific method. So now we look at science as a knowledge management holon. Ideas, theoretical frameworks, principles, assets, and those assets are then applied in nature and society. And these are the feed forward and the feedback mechanisms across across science as a whole. Yeah. So, and I've given some examples of this. So, an idea is a holon. Holon is used in the relational theory model. Understanding the relational theory model allows us to appreciate that everything follows a life cycle in the universe. In our systems engineering, we use that understanding in our life cycle management processes, and when it comes into just everyday life, we simply know that this is the way of things. Are you all with me so far? So another way of looking at this, ideas, frameworks for understanding, projected impact principles for deciding, intervention assets for acting, So we need to have a common language of systems. This recognises universal patterns of organisation. Then an understanding of the natural laws about systems. And from this, we can be better prepared to direct energy and resources. So that's kind of like an introduction to system science and the subject. And now I'm going into how do we organise knowledge about systems. So we have categories of knowledge which we've drawn from classical philosophy. So ontology, metaphysics, cosmology, praxeology, axiology, and epistemology. Identity, character, life cycles, capabilities, values, and learning. Those are the knowledge categories. Now, when we place that in a frame against essentially the stages of knowledge, so we've got concepts, theories, principles, assets, and the context of the whole, we have life cycle knowledge, which I explained just a few moments ago. And now if we add on identity, character, life cycles, capabilities, values, and learning, I change character to behaviour, because behaviour is actually a better way of thinking about it. And the other thing about learning is that not all systems learn, but all systems have an experience. So this category has more utility. So I've changed the work from David Rousseau into, I've changed character to behaviour, and I've changed learning into experience, because all systems have an experience, even atoms. I draw on fit, form and function. So the engineers in the room may have heard of this heuristic. So we have the form, the function and the fit. So within the form we've got things like identity, characteristic, structure and behaviour. In the function we've got things like place, purpose, life cycle and capability. And then we've got the why, which is the constraints on the parts, the affordances for the part, the environment for the part and the context of the part. So fit, form and function, it actually relates really well to this overall frame. So the concepts of identity and behaviour relate really well to form. With fit, you've got the value and consciousness of the whole, and the function is essentially a continuous dialogue between the part and the greater whole. What I've now done is I've added in candidate content into this overall frame. So in the concepts, we've got the key words and things that we use when we communicate and get an appreciation of systems. And I'm not saying this is completely right, but this is just to give you an idea of what could be slotted in there. We would have theories in that particular column, and then from those theories we would be able to derive principles based on those theories. And again, I've put in some content from George Mevis's work, his Systems Principles book, and just look at a couple of these. So this helps us to understand that simpler things combine into more complex things. Everything follows a life cycle. Value increases when stakeholders are engaged. The more complex something is, the richer is its experience. Yeah. And then we've got some classical knowledge from various different taxonomies from founders and others related to this content. So that's how we organise knowledge about systems, our general knowledge about systems. And then that helps us to put into context all of these things that the founders were saying. And there's a connection between those points and the content in that frame. And now, how do we organise knowledge about how we engage with systems? So again, I'm using the relational holon again as a foundation. But one of the starting points for developing this overall frame was our understanding of general system pathologies. So I talked about the problems we see in the world and the problems we see in our programs, and we did some work in the ISSS looking at these general pathologies. And we've arranged these general pathologies in the context of the relational holon, and that will become clear as we go through. But this is the real life stuff we see every day in our work. And the job of the systems engineer and the systems thinker is to address these pathologies. In the context of the relational holon, we've also identified what we're calling 9 transformational powers, drawing on the work from Bill Smith. And if anyone is familiar with Pestle, Pestle is the centre and the right-hand side of this diagram. In addition to Pestle, you've got the power of spirit living, philosophy and theory. So we've got the more conceptual over here, you've got the more sort of structuring aspects over here, you've got the what you might call the affordances for practice over this side, and then you've got the actual implementation of the system over here. So, you know, the resulting system and its design aesthetics and its impact on society. So when we overlay the transformational powers onto that knowledge about systems provides context for all of this. So theory is over that end, design aesthetics are over here. And the transformational powers help to address these pathologies. They're the motivators of change, if you like. Now, what we've also done is we've looked at least 20 different works on systems thinking, and what we've tried to do is we've tried to identify the pathways of systems thinking and systems practice which address the pathologies. And this is the map we created. So what you've got is you've got on the edges and in the centre you've got the transformational powers, you've got the pathologies in the centre, and what we've done is we've mapped on lots of different works of systems thinking, and we gave voice to the actual pathways. So these are the pathways in the context of the pathologies. So we've got emergent signals down there, new perspectives and knowledge being developed, new know-how, implementation potentials and experiencing systems, parts and wholes. And if we look into the centre, the political power has the capability to resolve these pathologies. No vision of the future situation is resolved through giving voice to future possibilities. Not seeing the connection flow of causality is addressed by planning ahead. You know, those kind of things. So these are the positive pathways. But as we all know, there are negative pathways which actually cause these pathologies to come into place in the first place. So again, if we look in the centre, reluctance to change, manipulation of information, benefits to the parts and not the whole, which we know as corruption, and manipulation of relationships. So these are the negative pathways. Now, when we apply systems thinking, we apply a systems approach. Again, this is candidate. These are the actual work products, the products of being systemic. And again, these help us in our everyday work and in our systems engineering and in our project management. These are the things that we actually create within that overall frame of the general human activity system. So within that overall frame of the general human activity system are actually 24 transformational pathways, individual systemic reactions, if you like, which are reversible. And this is one example of, you know, and I've called this one what might be. So you've got the pathology, which is no vision of the future situation. You've got the political power, which can be used to promote reluctance to change, but it can also be used to promote giving voice to future possibilities. Yeah. In order to give voice to future possibilities, we have to create the vision, the mission, the objectives with the key stakeholders. But within that space, you've got concepts, frameworks, you can derive principles, and we have our assets. So what assets do we have in this space? So this is one example. In this particular space, we've got stuff like stakeholder influence maps, the as-is and to-be analysis, the problem and opportunity statements, and the process that we're applying in this space is business and mission analysis. So we can take our 34 ISO 15288 processes in our international standard, we can look at them again and frame them in the context of the 24 transformational equations, and we'll be able to better to construct our ISO 15288 processes as an actual system. because at the moment there are some gaps, there are also some duplications. It was created bottom up based on heuristics. Now using system science, we can actually relook at that framework and maybe do it better. But this is also a way of organising our knowledge, because we have a massive diversity in terms of know-how and experience. And if we could better organise that, then I believe we could actually be better at doing project management and systems engineering. So we've got knowledge about how we can be systemic, and when you look at the 24 pathways, you get something which looks like this. So my vision for the future is that we have, I believe now, a way of at least organising our knowledge coherently. And when you take individual bits of knowledge and you put them into the same space, you can start to see the relationships and the synergies across them. Yeah, so our project management and our systems engineering processes don't have to be combative. They can actually be complementary, and we need to be drawing on that. Okay, so how am I doing for time, Cliff?
Yeah, you're fine.
How much time have we got left? How much time have we got left?
What time is this over?
10 minutes, I think. Okay, so I'm now going to fairly quickly go through putting it into practice on programs. So one of the key concepts I talked about was life cycle. And this is a typical project life cycle where you have to invest at the beginning in order to achieve the benefits over time. Yeah. And it's a very useful model for managing the complexity of our project's delivery. Now, the one key question is, when does systems thinking start? And when does the project actually start? Because the traditional view on project management is the project manager is responsible for time, quality, and cost. But you don't know when that is until this point, until you've gone through the estimating funnel, until you've done the conceptualization, the feasibility study, the planning, and the actual launch. Until you've got to that point, the project scope isn't really clear. So systems thinking, well, first of all, it doesn't just stop here, but this systems thinking over there is incredibly important. Because what we tend to see on our programs and projects is you have this proposal phase, which is led by marketing and sales. They agree a contract, which looks like that, but then the project manager comes on board, and then the project manager is trying to hold to this, but it turns out that it's actually this. And this is why the systems engineer and the project manager have such a clash, because the systems engineer is trying to produce a solution which is actually fit for purpose and meets the stakeholder needs, but the project manager is desperately trying to hold on to the scope. And of course, that's going to lead to conflict. We have the same kind of problem towards the end of the project as well. The project manager wants to get rid of that damn project, yeah? And then you end up in an operational phase, and what you deliver is not fit for purpose. And we see this in things like the Millennium Bridge, for instance. Yeah, this is why only 1% of our projects actually succeed. We've done some work using a framework called COSYSMO. It's a cost model for systems engineering. And we've been using the model retrospectively to look at the cost of assumptions. Yeah? So what's written in red here is the assumptions made prior to contract, and the blue is what the reality turned out to be through the project experience. This was a project that actually went really well. It was only 20% over budget. And the reason was there was a difference in architectural understanding. This project was more problematic. The difference was vast. When you take together all of these different factors, COSYSMO predicts an increase in cost of about 500%, and that was what was actually experienced. And this is not just a problem in aerospace or defence and space. It's not just a problem there. It's a problem everywhere. In power, in infrastructure, in everything that we do, you get this same kind of problem. Because this understanding phase at the front end is so important. So if you're involved in programs and projects, explore, think, test assumptions, iterate in your planning continuously, and then think again, because you won't really know what you're going to implement until you've gone sufficiently through that cycle of understanding. And this is what it feels like in terms of technical debt. Yeah? If you minimise your bid effort and in engagement with the customer at the front end, the kind of technical debt you're taking on is through a loan shark arrangement. Yeah? We should be at least heading towards the yellow and ideally the green. The green is what you might consider to be a more product-orientated approach. It's where you're reselling solutions. That's where, or reselling ways of working. You're not reinventing the wheel every time you do it. Another massive impact on your effectiveness and efficiency is your organisational quality. How well is your organisation geared up to actually deliver the programme? How good is your stakeholder team cohesion, your team capability, your experience, your process capability, your multi-site coordination and tool support? These all have an impact. So if you're trying to establish an organisation at the same time as you've started to deliver a project, again, you are doomed. Yeah? You have to have all of this set up before you actually start. It's another nice piece of work from the PMI INCOSI MIT Alliance. This was the Guide to Lean Enablers for Managing Engineering Programs. This is again a really nice multiple cause and effect diagram. And from this, a key point I want to emphasise is poor acquisition and contracting processes will lead to insufficient programme planning, which will then lead to firefighting and reactive programme execution. Systems thinking helps to address this. I mentioned Bud Lawson. Bud Lawson gave a talk in the IEEE quite a few years ago before his death. And this is something that I've been using, not just in system science, but also in my everyday work in terms of technical management. So he takes the OODA loop and the plan, do, check, act loop, and he integrates them together. So you have continuous situational management taking place. And again, those are instantiations of the relational holon. One is a strategic holon and one is a tactical holon. When you're preparing your what traditionally is called the systems engineering management plan, but I call it the technical management plan, when you're putting together the technical management plan, these are the kind of things you have to be doing. Understanding what the purpose is, analysing the stakeholder needs, analysing their concerns, assessing the scope of the task, assessing the complexity and risk, using COSISMO as a helpful thing, defining the technical strategy, all of that stuff. Yeah, that reflects the mode of thinking you go through. And we see this in our technical management processes. So again, we've got the OODA loop and the plan, do, check, act loop. So you've got establishing the organisation essentially at the top. Here you've got the leading the team, and there you've got strategically reviewing your baselines in terms of those life cycle events. And for those of you who know about Agile is all about this stuff over here. Here's your sprints and your scrums and your daily stand-ups, making sure that everything that you're doing is coordinated and issues and risks are being dealt with proactively. So this is your day-to-day management. This is your strategic review every couple of months or so. Your planning activity is something which has to take place on a daily basis. If you're going to achieve this, you have to really be focusing on situational awareness. Donella Meadows' leverage points also come into this as well. So, this stuff here in terms of her leverage points relates back to our knowledge about systems and how your knowledge about systems can help you to identify appropriate leverage points. By applying systems thinking, we can turn that diagram on its head, and now we've got smart business and acquisition contracting processes leading to effective planning and all of these positive things which eventually lead to projects that enable good and profitable business. But again, this is, a relational holon. I'd like to emphasise the importance of that situational awareness again, and being aware, being persuasive, being constructive. If you know you're on that purple curve, you can still do something about it. You may not be able to recover the entire situation, But you may need, if you realise you're in a bad way, do a project restart, do the right design, plan for the right implementation, and then you can avoid an awful lot of this. But that takes guts. It also takes persuasiveness, because the stakeholders won't want to listen.
We have the room till 1:30, so.
Oh, okay. Well, that's good, because we'll have some time for questions then. Okay, so this is the last slide. I'm just going to give voice towards applied systemics. So some of you may be aware of the Kinefin model. David and I don't exactly see eye to eye on all of this, but he said it was a worthy attempt. Yeah, and from David, that's pretty good. Yeah, so we've got the chaotic, which is where we're working out why, the complex, which is working out what, the complicated, which is working out how, and then we've got the establishment of wisdom and making things clear. Now, when we look at at science, on top of that, first of all, we've got information and observation down there. Knowledge and architectural appreciation is what you need in the complex area. Power and forces are elicited through your design. It's working out how you're actually going to do stuff. And then you've got the manipulation of energy and mass with your realization. In terms of system science and our systems community, our enterprise of system science, we need a common vocabulary. And that common vocabulary comes with an understanding of all of those core concepts which are transversal and how they are organised. We ourselves need to get organised in terms of our overall enterprise. All of the systems organisations and all of those organisations which have systems sensibility need to be collaborating together within a shared orientation, and that's the value of an integrated framework. Once we have that as a basis, we can then start to collaborate much more effectively, and we can get out there and do more good. And we can create order from disorder. That's it. So, any questions? If you'd like to communicate with me privately or engage, you can find me on the ISSS website, the International Society for System Sciences. If you'd like to find out more about system science, it's also a great place to look. You can also take a look at the Systems Engineering Body of Knowledge. There's some really amazing resources on there.
So, here's a question right there.
Let's see if I can articulate this coherently. So, within your framework, we've seen a number of stories recently of what I'll call broad systems failures, and without attributing it to any company or anything, we've seen issues with hatches in aircraft, flight control systems, and it seems like those could be traceable to, in some cases, mechanical things, maybe some cases organizational or socio-political things. In your experience, how would you overlay some of our lessons learned on this structure?
Okay, so lessons learned comes down here, learning from mistakes.
Perfect.
Yeah, and generally we don't. Yeah, we have what we call lessons learned reviews, but all you're doing is really identifying what you should be learning. Unless you have processes for actually then taking that into account, then you're not going to learn the lesson. It might remain with individual people, but organisations don't learn.
I have two questions.
Sure.
You mentioned briefly about like having structure and some form of abstraction as well, in terms of like philosophy and design in general. So I was wondering, like, with that abstraction comes some form of appreciation towards the humanities, if you're talking about philosophy. So like, can you comment on the competency that's required for a systems engineer to actually have, like what is the real competency of a system engineer? Is having that structure and also abstraction?
Yeah, systems engineers are, David Long says that systems engineers are weird. So they're able to, they are full of, I think it's dichotomies, yeah? So they're able to dive into the detail, but they're also able to see the big picture as well. They are often introverts, but they're able to be extroverted as well. They're able to be thinkers, but they're also feelers. Yeah, so they and this is just my view. Yeah, I don't think. So first of all, there's a place for everybody in this framework. Systems thinking is not just for the systems engineer. System thinking is for everyone. From my perspective, there are lots of different kinds of systems thinking. The kind of systems thinking that we should be doing over this space is a different kind of systems thinking that we do over here. It's just a different emphasis. You need, I know that the scientific community have a downer on things like Myers-Briggs, for instance, and personality traits. But actually, those personality traits are really quite useful to understand. The work of David Snowden and his team roles. Not Dave Snowden, David Belvin, and the team roles, that's really useful. Now, the reason why we have that diversity in terms of traits, characteristics, is because those traits, that diversity, is actually advantageous to us as a species, because we need that full diversity in order to be successful in engaging with systems. So when you do an analysis of Myers-Briggs and Belvin, the character traits, again, fit across the whole. And I don't know if you know Carl Jung and Jungian theory, but you've got introversion over that side, you've got extroversion largely over here, you've got thinking at the top, you've got feeling at the bottom, and those traits map really well onto this as well. There's an awful lot of knowledge which maps onto this stuff. The Tao Te Ching, for instance, it's a work of Chinese philosophy, 3,000 years old. The 81 chapters is a more detailed instantiation of essentially these positive pathways. We've got 24 positive pathways here. The Tao Te Ching is 81 positive pathways, and they've been mapped onto this as well.
Yeah.
Second question.
Yeah, second question. It's very rare for me to meet somebody who's a member of IEEE Systems and also like ECOC. And both of these organizations have arrived on different definitions of what system engineering is. This may seem like a trivial question, but somebody has asked me this question before. Which definition do you believe in, and what it means to have like a common vocabulary between the two definitions? Well,
so I'm not familiar with the IEE one, I must admit. So the INCOSE one is pretty good. It's and I'm not going to quote it because I'll get it wrong. Yeah, but one of the things one thing which is missing in the INCOSE thing is it talks about the whole has meaning, but the parts individually do not. What they're missing in that definition is meaning in the context of what? It's the environment. Yeah, the Bogdanov's definition is much richer. I haven't got it in here, but Bogdanov basically talks about the continuous dialogue between the parts and the whole.
So INCOSE has it now as a transdisciplinary approach to the realization of successful systems, and then they add more to it.
Yeah.
And I have to say, the IEEE definition does not have any word of transdisciplinary.
No, and INCOSE is fairly new, I think, in making that term part of the definition, where it wasn't there in the earlier approaches. So.
Any other questions? I'll show you something else if I can find it quickly enough. Yeah, I did a talk in the ISSS a little while ago, and
The ISSS is the International Society of System Science.
yeah. So we did an analysis of these various definitions of system, because there is a massive diversity out there. Yeah. The best one, from my perspective, Bogdanov's system or complex is not simply a collection of aggregate or vector of components and their relationships. A system is a process or continuous flux of independent component producing processes concatenated in self-triggering cycles of build-up and degradation. Bogdanov's system cannot be separated from its environment because it does not simply exist or interact with its environment. It is structurally coupled with its environment and thus evolves its own environment while co-evolving with it. So what we found is it can go from simply a collection of two or more parts, a collection of two or more related parts, it forms a whole. Novel properties emerge, cannot be divided, and then is part of a whole. So these are lots of different definitions of system in terms of richness. I think the most advantageous definition is at the bottom, recognizing that systems are integrally coupled with their environment. You cannot simply just look at a system and say, that's what it is. You have to think about its context.
I think when it comes to the terminology in this field and related to systems engineering, without the structure and the framework for how you're even structuring this whole field, it becomes hard to have that terminology that's consistent because people will just take it from where they think, and maybe a committee puts it together, maybe they have a thinker that put it together that they all admire, so you never know where that came from. But with this kind of structure, you can start to have a more consistent knowledge base that provides this, the way to communicate in that terminology.
We have Mary Edson is holding her hand up online.
Yes.
Is there a way of allowing her to speak? Hi Mary, can you unmute?
Hi there, yes. Hi Gary, hi Cliff, how are you?
I'm great, I'm glad to see that you're okay.
Yeah, we've had some adventures here. I really enjoyed your presentation, Gary, and I guess what I love about the presentation and how you've related all of these concepts and ideas is how it relates to Aristotle's four causes. And I guess you and I have talked about this. Systems engineers are really, really good at the material and efficient causes, but there are opportunities in the formal and final causes for systems engineers to really step into leadership. And you identified one of those things as being the contracting phase. Yeah. And I'm kind of wondering what your thoughts are about, in practical terms, how systems engineers can become more involved in contracting so that they can anticipate where there may be gaps in the contract and prevent or at least mitigate some of the fallout from any kinds of, I guess, misinterpretations between the client and the contractor, so that more projects are coming in successfully.
Yeah. So I think in part, again, it's a cultural change, because at the moment, that early engagement with the clients is led in some cases almost entirely by sales. Yeah. And there needs to be a recognition that the architect is the person who should be leading those thought engagements with the customer. But that means that the architects have to have the right kind of personality and wherewithal so that they're able to have that customer engagement. It's not just a case of being brilliant, you've got to have personal skills as well. And then maybe the salespeople won't be so scared of letting us talk to them.
Yeah. Well, thank you.
Thanks, Mary.
Do you have an idea of, in real projects, perhaps, for example, the book of mega projects you mentioned, when they fail, which areas of the framework they most typically fail on? And is it like a cascade?
Yeah, from all of the analysis we've done, it is that overall understanding of the problem and the big picture of the solution that's missing. Yeah. So when we do our engineering, our architecting, there's two key things that really come out of that essential work. One is the functional breakdown structure, and then related to that, the product breakdown structure. Unless you've got a really good understanding of those things, how can you on earth have an understanding of the cost breakdown structure and the work breakdown structure if you don't understand those fundamentals of what it is and why it is required? Then your estimates in terms of the effort is going to be, as we've seen from the COSISMO, very wrong. Yeah. So, as Mary mentioned, you know, the final cause and the formal cause aspect of Aristotle's four causes, that's where we conceptualize and that's where we architect. And we have to put much more effort into increasing the maturity of those things before we go on contract. If you're making significant changes to your architecture and your overall conceptualization after the contract, then you're going to be in a mess.
So see, I just had wondering, in a large organization, and like Airbus or any other large organization you've been in, how do you operationalize systems thinking into the organization as a culture change or as training, education? Because it's probably a big.
We've not done it yet, to be honest. We've not done it yet.
Yeah.
Yeah, that's one of the things that's one of the things I have to do. That's part of my job.
Well, you got your work cut out for you. Any other questions? Fine. Questions?
Okay, thanks a lot, everyone.
Yes, okay, thank you. And thank you, Gary.
Thank you.